So last time, what did we talk about? So last time we sort of started with root finding. Then we talked about Newton's method. As sort of the gold standard kind of numerical method for solving root finding problems. And then we talked about minimization as sort of the, and how specifically how we like more or less transform minimization problems into root finding problems by writing down their first order necessary conditions, AKA set the gradient equal to 0. And now you can solve that gradient equals 0 root finding problem with Newton's method, right? And we did a bunch of stuff with that. We did a couple examples, and we talked about some of the hacks you need to add to Newton's method to do what's called globalization, to basically make it work when it's far away from the answer on a nonlinear problem. Specifically, we talked about regularization. And then we still have one more little thing to talk about, which we're going to do right now, which is line search. And then today, we're going to talk about constrained minimization, constrained optimization. So we'll do the line search thing real quick. And then we're going to get into constraints. All right, any questions about anything? Okay, so just to refresh our memory from last time, I'm gonna go ahead and switch back to that Jupyter notebook. So if you guys remember, this is from last time. This was with regularization, right? So we started kind of over here, remember, and then without regularization, it went and found the local maximum, which we didn't like. So we talked about adding regularization to make sure things go downhill. So we did that. And then after we added regularization, we found that it went the right general direction, but it overshot the minimum, right? It went way too far. And we didn't like that either. So we talked about how we should do something about this overshooting problem. And the something we're going to do is called a line search, specifically a backtracking line search. We're going to kind of go through the simplest version of this. So let's do that right now. Okay, so basically, in a lot of cases, if a function is highly nonlinear and kind of very curvy, you can have your delta x step from Newton's method be too big. Okay, so the sort of again, kind of a simple modification to Newton, kind of a little bit of a hack to fix this. And what we do is basically check our function evaluated at the new point, and then backtrack. And what I mean exactly by that we'll do in a sec. Basically chop the length of the step down until we get a sort of, in quotes, good reduction in our function f. So that's the general idea, the general intuition for this. There's a lot of specific implementations of this. There's a lot of kind of strategies you can use to do this. We're going to talk about one that's sort of the simplest one that works, basically. So this one in particular that we're going to do is called the Armijo Rule. Okay, so here's what this looks like. So when we evaluate our Newton step, we get our delta x. Then we're going to start out with a step length that we're going to call alpha. We're going to start this out at 1. So this would correspond to taking a full Newton step. And then we're going to check this following thing. So f of x plus alpha times delta x. So we're just shrinking the length. Alpha is a positive scalar, right? We're going to check this. And while this is bigger than, remember, we want this to be small, but we're going to check it against, you might imagine just checking it against f of x. So the previous value. Turns out that's not quite good enough to avoid zigzagging overshoot issues. What you want to actually do is check it against the first order Taylor expansion of f. So you want to check it against f plus this term that we'll write down real quick. And I'll explain in a sec. Okay, so what this term actually is, a couple things in here. So this b is a tolerance. And then this term is just the expected reduction in f given a first order Taylor expansion, right? It's basically taking the dot product between grad f and alpha times delta x, right? So this is like the naive expected reduction that you would get in f of x just if it were a linear function, if it just had the gradient. So what we're going to basically say here is, right, we want f of x plus alpha delta x, like this, our new Newton step with this sort of backtrack parameter alpha. We want this thing to be smaller than f of x plus, we want it to agree with the reduction we expected from a first order Taylor expansion within some tolerance b. And while that's not true, we're going to chop alpha down by some geometric factor c. And this is some scalar between 0 and 1. Okay, and sort of end. So, okay. Intuition for this. And if anyone has questions on this, feel free to speak up. So the intuition is, again, make sure our step agrees with the linearization within some tolerance. And that's a reasonable thing to do, remember, because we're using this linearization to compute the Newton step, right? So we basically don't, if these disagree by a lot, it means that the Taylor expansion we used to compute the step wasn't very accurate at that point, right? So it's maybe bogus. Okay, so that's kind of the intuition. And then typical values for the hyperparameters in here would be, so usually we've got sort of C, the factor by which we chop down the step length, usually set that to like a half. So basically just chop the step in half each run through this. And then typically the tolerance B is actually really small, like somewhere between 10 to the -4 and like 0.1. Okay, so let's go ahead and try this out. And again, feel free to speak up with any questions while we're switching back and forth and stuff. Okay, so this, remember, was what we saw last time. We got this big overshoot. Now we're going to go ahead and do this with the backtracking line search. So here's this implemented. We've got the regularization in there, just like last time. So we already did that last time. And then here's the line search. This is exactly kind of what we just wrote down. You start with a step length of 1, i.e. full Newton step, so alpha equals 1. And then we check the function at the new step, and we make sure it's smaller than this first order Taylor expansion within this B tolerance. And here I've set B to 0.1, C to 0.5, and yeah, the rest is the same as last time. So this is exactly what we just did with the particular parameters of B equals 0.1 and C equals 0.5. So let's take a look at that. So we're going to start at the same spot. And now what happens with this backtracking line search, rather than overshoot the min, we get a really nice step almost to the minimum, right? So that's 1 step, 2 steps, 3 steps, we're there. So this gives us nice, robust convergence. So adding the regularization, make sure we go in the descent direction, and then adding the line search, make sure we don't overshoot the minimum. And in general, you want to add both of these things when you implement like a real kind of a real version of Newton's method to solve nonlinear problems. You kind of in general need both of these. There's other ways. Yeah.
Would it make sense to? So I like the intuition for this one, but what if you wanted to instead do like a binary search instead? Would that make sense as well?
So binary search is really slow. And in general, this Newton stuff is dramatically faster. It's actually like not uncommon, like so we call these like regularization line searchy things globalization strategies, because Newton's a local search method, right? And so if we want to, if we're really close to the answer, Newton works great, but if we're far away, it kind of can break in various ways. So these are two different globalization strategies that work really well in general. Binary search is another globalization strategy you can use to globalize Newton's method. And in that context, what you might do is you start with binary search, and then once you've gotten close enough, you would use Newton at the end inside your last sort of bracket. Does that make sense?
Yeah. I guess the thing I was suggesting was that like instead of just strictly decreasing alpha, you could like maybe like half it and then find that one side of the interval is actually better, like if that would converge faster.
So in general, not actually, yeah. So the idea with this again is that you need these things when you're far away from the answer. Once you get close to the answer, you pretty much don't need either of the, like basically it just works when you're sufficiently close. Okay, so you're really only doing these things for the first few iterations. Once you're in the ballpark, it's super fast and all this stuff kind of drops out.
Yeah, that makes sense.
So yeah, usually spending a lot of effort finding the exact right alpha is totally not worth it. In general, there's like an optimal alpha, right? And you could solve a sub-optimization problem over alpha, right? To like find the best alpha, but it turns out it's just usually not worth it. And usually you just kind of chop it down by some factor until it's good enough and then go. Because again, once you're close, it doesn't matter anymore, that you don't need it. Does that make sense?
Yep, thanks.
Yeah, so you can do more complicated things for sure. Sometimes it might be worth it, but usually it's just not worth it. And this sort of strategy works fine. Okay, cool. So that's the line search story. Sort of final takeaway, sort of notes on that.
Hey, Zach?
Yeah.
Does the alpha get reset to unit length at the next time interval?
Yeah, so at each Newton step, at each outer Newton iteration, you would, it starts back at 1, that's right.
Okay.
Yeah, for every Newton step, you start at the full Newton step and then backtrack only as much as you have to, right? Okay, so final sort of takeaway messages. Newton is local search, but with these kind of simple, cheap modifications. Commonly called globalization strategies. It's really, really effective at finding local minima of functions. It's very, very fast. It's kind of the main thing. In fact, with regularization and backtracking line search, you can prove that for sufficiently smooth functions from any initial starting point, you can guarantee that Newton, with these globalization strategies, is guaranteed to find a local minimum, which is about as best you can do on a non-convex function. So super effective, super fast. In particular, this is way, way faster than gradient descent, right? Like a handful of iterations will get you there. Okay, cool. So good on that. Anyone has any questions, feel free. We're gonna now kind of switch gears and kind of do the next major topic, which is gonna be handling equality constraints. We're gonna get into constrained optimization.
So how is this related to like the quasi-Newton methods like BFGS, etc.?
So which thing in particular?
So like the idea of using line search first and then going from there and then doing the Newton step once you look.
Well, so to be clear, right, you take a Newton step, and then if it's too big, you backtrack with a line search. So they're sort of, you can do a line search with any optimization strategy. Basically anything that gets you a step, you would then potentially backtrack on that step, right? So however you get the step, whether it's from a full Newton or from a quasi-Newton method or even gradient descent or accelerated gradient descent, any of these methods, right? They all give you a step, also called a search direction. Any of those you can apply a line search to. Does that make sense?
Yeah, cool.
Cool, all right. Okay, so here's what we're gonna do now. So before we had, right, this sort of thing, min of some function f of x, where f of x is from Rn to R. And now we're going to add something new to the mix. We're going to do this problem subject to some other function, c of x equals 0. And this is we're going to call it constraint, right? And c of x is a function from Rn to Rm. And what that really means is we have m constraints, right? So c of x is a vector function. It eats the vector x, and it spits out a different size vector. And all that different size vector is the output of this guy is just take all the constraints you want, write them down, and stack them into a big vector function c, right? So we have m individual constraints. Okay, so now we're going to talk about first order necessary conditions for this problem. And first, intuitively, we'll talk about what they are, and we'll kind of try to write them down mathematically. So first order necessary conditions. So the first one is a simple sort of modification of what we had before. We want the gradient to be equal to 0, right? We want a flat spot, but in this case, the extra little wrinkle is that gradient has to equal 0 in the free directions. So what that means, right, is if I have a constraint, I can't move in that direction, so I can't do anything about it, right? So I only want to require that the gradient equals 0 in the directions I can actually move, the unconstrained directions, right? Does that make sense to everybody? So gradient has to be equal to 0 in the free directions that I could actually move. It doesn't have to be, in general, won't be it'll be non-zero. You'll have some non-zero gradient in the directions that you're in the constrained directions, right? So like normal to the constraint surface where you can't move. And then in addition to that, we need the constraint to be 0, which is kind of obvious. Okay, so let's draw a little picture to sort of like motivate this a little bit. So let's say I have a 2D function f. So f of x is from R2 to R. And I'm going to draw like level curves of this function, right? So it's some kind of bowl shape. So here's sort of the level curves of my bowl. And let's say it's got a minimum at the origin or whatever. And then similarly, C of x is also going to be from, it's going to be a one-dimensional constraint. So I can't really do anything else here and have it have any free directions left, right? Okay, so these guys are level curves of f. And then let's draw the constraint surface, C of x equals 0. Let me draw that like over here. Okay, so what we're kind of saying, right, this, so another way of saying like grad f equals 0 in the free directions, sort of the opposite way of saying that, or sort of a totally equivalent statement, right, is that any non-zero component of grad f has to be normal to the constraints, has to be basically in the constrained directions, right? And I'm going to use the words sort of surface and manifold interchangeably, or manifold's kind of like the higher dimensional version of a surface, right? Okay, so here, let's draw some little arrows for these guys. So, you know, here's gradient of f here, right? Here's another gradient of f. And then for C, its gradients, right? The gradient of C are these normal vectors to the constraint surface. I should probably use a different color for that. Let's do that with green, say. So here's grad C, for example. And then if I write, so intuitively, if this bowl has a minimum at the origin, the solution to this constraint problem is going to be the closest point on the C of x equals 0 surface to that minimum, right? So intuitively, that's somewhere around here. And in particular here, what's going to have to be the case, right? At that point, my grad f looks like this. And so it's non-zero, right? Obviously. And what's true at that point, though, is that grad f has no component parallel to the surface C of x equals 0, right? It's totally perpendicular to it, right? So this sort of being 0 in the free direction is equivalent to being non-zero only in the perpendicular direction to the constraint surface. And so if we write that down in math, it looks like this. Grad f plus, we're going to add this scalar thing called a Lagrange multiplier, lambda times grad C equals 0. This has to be true for some lambda. Which is a scalar, right? And we call this lambda thing. So this is really just a mathematical way of writing down grad f is parallel to grad C, right? They have to be parallel. They don't have to be the same length. So this is saying grad f, grad C, they can have different lengths, but you know that's what the lambda takes care of, right? The lambda is just matching up the lengths between these things so that it equals 0. So that's how we write down parallel, basically. And then this lambda thing we call Lagrange multiplier. Or sometimes dual variable is the other name for this thing you'll hear. Okay, any questions about that? We're good with that. Okay, so this we kind of did the scalar version in general and sort of higher dimensions. We write this sort of thing: partial f partial x plus lambda transpose partial c partial x equals 0, where everything can be, whatever dimension. And lambda, what's the dimension of lambda here? So lambda, remember, if we have C from Rn to Rm, we have M constraints. What's the dimension of lambda? Someone help me out. Yeah, it's M dimensional. Lambda has the same number of dimensions as we have constraints, right? Because that partial C partial X Jacobian is going to be M by M. So that multiplication has to work out. Okay, cool. All right, so moving on then. So based on this kind of geometric picture, this parallel gradient kind of idea, we're going to write down a new function. Kind of for convenience. L of x and lambda, this thing we call the Lagrangian, which just combines the objective with that Lagrange multiplier and that constraint function. Okay, so this guy is called the Lagrangian. And the reason we define this thing is that it very conveniently works out that this thing's gradient is the root finding problem we want to solve in the constrained case. So in particular, if I look at this Lagrangian function, if I take its gradient with respect to x, I get grad f plus partial c partial x transpose lambda equals 0. Set that equal to 0. And then if I take its gradient with respect to lambda, I just get back the constraint function, which, remember, I also need to be equal to 0. So conveniently, by smushing this all together into one function, I just get gradient of L with respect to all its arguments equals 0. And we call this set of conditions Kkt conditions. These are sort of the first order necessary conditions for a constrained optimization problem. Although this is for, it gets more complicated for the inequality case, which we're going to talk about next. But technically, the Kkt conditions are the inequality version. The equality version, which is simpler, people still call it that. So we might as well call it that, I guess. Okay, cool. So then here we go. We got these first order necessary conditions, these gradient equals 0 plus constraint equals 0 sort of conditions. Now we have a root finding problem again, right? And what do you know? We're gonna solve that with Newton's method, right? Okay, so let's look at that. So in particular, right, these are nonlinear functions in general. So we have to take a first order Taylor expansion like before. We're gonna do first the grad with respect to x1. We're gonna plug in x plus delta x, lambda plus delta lambda. So we're gonna take a first order Taylor expansion in both variables, right? So this is approximately the original sort of function plus partial with respect to x of this guy, which is the now second partial derivative with respect to x, aka the Hessian, right? So this is going to be partial squared L partial x squared times delta x plus now this like mixed partial, right? So partial squared L partial x partial lambda. times delta lambda. And it turns out, if you go and take this mixed partial, if you go look back up at the Lagrangian and take this mixed partial, this is just the constraint Jacobian, right? Because partial L with respect to lambda just gives me back C of X. And I take that thing's partial with respect to X, I get partial C, partial X. So it turns out in particular here, this is partial C, partial X transpose. Okay, and then we do the other one. Grad respect to lambda of L of X plus delta X, comma lambda. It turns out this one, right, doesn't depend. We know what this one is, right? It's just C. So when I take this guy's derivative, it doesn't have a derivative with respect to lambda. It only has an X derivative. So this is a C of X plus partial C, partial X, delta X. Cool. So these are our first order Taylor expansions. Now we're going to sort of smush all this together into a big matrix linear system that looks like this. So we get from the first row, we're going to get partial d squared lambda dx or L dx squared. So the Hessian of the Lagrangian. Then we're going to get partial C, partial X transpose. That those guys multiply delta X, delta lambda, right? And then on the other side, we're going to get minus grad X of Lx lambda. So this is literally just me writing this first line, right? I'm just moving terms around and writing it out as a matrix vector equation, right? And then the second one is just partial C, partial X times delta X. There's nothing here, right? Equals minus C of X. Okay.
Professor?
Yeah.
Why the mixed gradient here, or the mixed derivative is equal to dc over dx in the third line?
The second line in the matrix equation?
Yeah.
So literally that's just this equation here. So all I did, right, was I moved things over. So I moved the so this equation says partial C, partial X times delta X equals minus C of X. Right, so it's this equation set equal to 0. Sorry, both of these should be set equal to 0. Does that make it clearer? So literally it's just this sort of moved around. This says partial C, partial X, delta X equals minus C of X, right? Is that clear?
Not really, but I was asking about the gradient of L with respect to X. In the last term, we have second derivative of L with respect to X and or lambda and X. And
yes.
We said that it's equal to first derivative of C with respect to X.
It is,
transpose. Yes. And how did we get that?
We get that from looking at this equation, right? This is the definition. Okay, so what's the derivative of this with respect to lambda?
Cx. Oh,
yeah.
Okay.
And then you take that thing's derivative with respect to X. Okay, partial C, partial X. Cool?
Yeah, thank you.
Okay, great. All right, so this thing, this linear system we just wrote down, this shows up all over the place in optimization. It's kind of super, super standard. And so it's so common that it has a name. This is called a Kkt system. So it's, in particular, it is the linear system that shows up when you do Newton's method on a constrained optimization problem. So when you write down Newton's method on the Lagrangian sort of first order necessary conditions with respect to both x and lambda, you get this particular linear system. And it's so common that it has a name, and lots of sort of specialized numerical methods for solving exactly this equation. So in particular, some things about it, right? The Hessian shows up in the top left, and then you have the constraint Jacobians sort of on the top right, bottom left blocks, sort of transposes. The whole matrix is symmetric and has some nice properties. So that's sort of worth knowing about. One more thing to say about this. So this is Newton's method applied to this constrained optimization problem. There's one more little sort of thing to point out about this before we go do it. There's a little bit of an approximation of this, a little tweak that's really common, especially in optimal control, called the Gauss-Newton method. And the idea there is, if I expand out the Hessian of the Lagrangian, so this guy, partial squared L, partial x squared, if I sort of like, dig into that and triangle it out or whatever, I get the Hessian of the objective. And then I get a term involving the constraints. And in particular, that next term looks like this, partial respect to x of partial c, partial x, transpose lambda. Okay, so it's literally just I took this guy, this gradient of x term, and I differentiate it with respect to x again, right? So I get del squared f, and then I get this derivative with respect to x of this second constraint term, right? Okay, so let's look at that second constraint term a little bit closer. So partial c, partial x, that's a Jacobian matrix, right? And if I then try to like apply the product rule or whatever and carry out this next partial respect to x derivative on that thing, you'll end up with second derivatives of that constraint, which end up being, in general, for vector things, a third rank tensor. And turns out this term is typically the most expensive thing to compute in a constrained sort of Newton step. And we don't like it. It's sort of annoying also for another reason that we'll talk about in a sec. So often we will just leave this one out and only put in the Hessian of the objective instead of the Hessian of the Lagrangian with this extra constraint curvature term. And it turns out, so when you do that, when you leave out that second term, it's called the Gauss-Newton method. And yeah, it's cheaper, and it turns out often in practice, it gives you slightly worse convergence behavior, but it usually wins in terms of wall clock time. Usually because the iterations are so much cheaper, even if you have to take a couple more iterations, it's usually still a win. Okay, so now we're gonna go do this stuff, and feel free again to ask questions when I switch.
I have a question about that simplification. Does it depend on the constraint though, if it's actually simple versus more expensive?
Yeah, so for sure. So like there are definitely situations where that term could be super cheap and you don't care and it's fine. But often in optimal control in particular, these constraints are our dynamics of our robot. And so if you're talking about like a humanoid robot and this being your like manipulator dynamics of some really complicated robot, computing like the second derivative of your dynamics is often really expensive. And so in that context in particular, it's usually not worth it. So it's basically the standard thing in optimal control to leave out that term and do Gauss-Newton. I would
that makes sense.
Yeah. All right, cool. So let's go do some of this. So here's our Julia stuff. So here's what we're going to do. This time we're going to write down a nice little quadratic objective function. So my f of x is like, I don't know, this guy here with this Q matrix smushed in between here. So this is my Hessian, right? It's a nice, and it's a nice little, made up function. So I can write down the gradient and Hessian in closed form like before. So I write all that down by hand right there. And now I'm also going to make up a constraint function. And here I also made up a quadratic constraint just to make it nonlinear, so it's more fun. And it's pretty simple. So I wrote down the Jacobian matrix of the constraint as well, all in 2D, right? So quadratic objective, quadratic constraint. And now here we're going to plot this kind of landscape. So it's like the picture I drew a second ago. So I have plotted a bunch of level curves of the objective, and it's like a quadratic bowl, right? We have a positive definite Hessian here, so the whole thing looks like a big bowl. And then this is my quadratic equality constraint, this yellow parabola, right? It's a quadratic function. And what I'm saying here is I have to be on the parabola, right? It's an equality constraint. So I want to minimize it subject to being on this parabolic surface. Okay, so let's go ahead and do that. So here's Newton's method. I'm evaluating the Hessian, and this is full Newton. So I've got the Hessian of the objective plus the Hessian, it's the full Hessian of Lagrangian, right? So this is that Hessian of the objective term. And then this is that second term that I said we often drop in Gauss Newton, but here it is, right? So I compute partial C partial X transpose times lambda. And then I'm using automatic differentiation, this Julia forward diff package to compute the Jacobian of that thing, right? So I get that kind of weird term. So that's my full Hessian. Here's my constraint Jacobian. Here's my Kkt system. So Hessian, constraint transpose, Jacobian transpose, and the bottom row, constraint Jacobian 0. Here's my right-hand side vector, right? So it's minus the gradient of the Lagrangian up top and minus the constraint on the bottom. Stack everything up. And then this is just, this is me solving that, Newton system, or that Kkt system, and then just pulling out the x and the lambda from that vector. And then I'm doing my update, right? So that's kind of exactly what we wrote down. Now let's kind of go do some stuff here. So I'm going to start it out first. Let's say here at 1, kind of the bottom, just kind of random starting point, not super important. And we're going to see what happens when I do Newton, right? So let's go ahead and do that. Okay, cool. So remember, I'm linearizing the constraint. So here, that linearization produces like a tangent plane that looks like this. And I'm going to minimize the function along that tangent plane, basically, is what Newton's doing. So this makes total sense, right? So I take this linearized surface, and I take and I minimize along that linearization. That kind of puts me out here, right, near the minimum of this objective function. So let's take another step and see what happens. So now it's pulling me back up towards the constraint surface because here, if I linearize here, the tangent plane looks like this. So kind of pushing me back. That seems good. A couple iterations. Third iteration. Now I'm back on the constraint. Let's see. So kind of 3-4 iterations, I'm there. And so intuitively, right, I want the point on the constraint surface closest to the actual, unconstrained minimum. So that looks about right. And you kind of see what Newton's doing, like intuitively, the behavior kind of makes sense. You're successively linearizing the constraint surface and minimizing along that linearized approximation of the constraint surface. Does that make sense to everybody? Cool. So now we're going to go ahead and do it with Gauss Newton. And it's all the same. The only difference is here I've taken out that constraint curvature term from the Hessian. So it's just the Hessian of the objective. Everything else is exactly the same, right? And we'll start at the same spot. And we'll go ahead and take some Newton steps and see what happens. Okay, so this looks exactly the same. Another step, back up towards the constraint surface, pretty much the same. 3, cool, yeah, like 4 steps. It looks exactly the same, essentially. If you really look carefully, this second step is a little different between the two. You can kind of tell, right? But they basically converge in the same number of iterations. They produce almost exactly the same behavior. So The message is they behave very, very similarly, and the convergence behavior is almost as good. In particular, if you want to get like very technical, Newton's method has like quadratic asymptotic convergence, but Gauss-Newton has superlinear, which is a little worse, but it's still very good. So might take another iteration or two, but you're going to get more or less the same behavior out of these things, and it's a lot cheaper. So that's kind of the message there. So that's both of them compared. We're going to now, let's go try something else a little weirder. So any questions, feel free. What I'm going to do now is pick a different starting point that's a little farther away. So let's try this guy. Okay, so I'm going to start up here. So farther away from the minimum, right? Remember we said there's all these kind of weird issues with Newton when you're far away, and we had to do this globalization stuff. So let's kind of look at what happens when I try this. So let's run Newton on this guy. Okay, one step, cool. I'm minimizing along the tangent. That sort of makes sense like before. Next step, cool. I'm kind of going the right direction, seems like. Next step, what's going on? Okay, so it looks like I kind of like went down here and then I'm moving back the wrong direction. And I'm like converging to some point sort of like around here, which is neither fully satisfying the constraints. So it looks like it's probably going to satisfy the constraints in the limit, but it's definitely not going towards what we kind of know is the minimum right over here. So that's kind of weird. Let's see what Gauss-Newton does in this same situation. So -3, 2. So same starting point. Let's run this a few times and see what happens. So same first step, pretty much the same kind of behavior it looks like, but as I run this one, it's kind of doing the right thing. It's kind of inching along the constraint surface towards this minimum. Kind of overshot there, but now look, it popped up into kind of exactly where we expect, and it landed at the right solution after like, I don't know, 5 or 6 iterations. Okay, so can anyone tell me what's going on here? So we said, all this stuff about Gauss-Newton's more approximate and should be worse. In this particular situation, it's doing better. It's converging to the right answer where the full Newton actually gets stuck and gives us a bad solution, right? Anyone have any thoughts on what might be going on here? Someone give me a guess.
Are we preventing it from overshooting when we take out that last term? Is that what's going on?
No, but so obviously the only difference is that Hessian term, right? So think about our conversation last time about regularization and like positive definiteness of the Hessian and all this stuff, right? So the objective here is a nice quadratic that's positive definite and all that stuff. So the objective's good. But this constraint curvature term that I'm adding to the Hessian and the full Newton is obviously doing something weird, right? And in particular, if I check here, I'm going to check the, let's see, make sure I'm, okay, we got to restart this guy. So let me run this a few times again and get to kind of where we were. Okay, so if I check the Hessian where I landed over here, where Newton got stuck, it's got a negative, this is again the Hessian of the Lagrangian, right? So it has the objective term and this constraint curvature term, and sure enough, it has a negative eigenvalue in it. So what this is saying is that even if your objective is nice and convex and positive definite everywhere, if you have nonlinear constraints, which we always will basically in like the stuff we're doing, or most of the time, right? Dynamics are usually nonlinear, at least for interesting things. That constraint curvature term that you're sticking in the Hessian there for full Newton can actually make your Hessian of your Kkt system become indefinite and have negative eigenvalues and do weird things. So that's sort of annoying. And that's yet another reason actually why it's super common in optimal control to just leave it out. It's kind of more trouble than it's worth a lot of the time. So in particular here, right, the other kind of takeaway message here is that on these problems, you very much still have to play the same games we talked about previously with regularization and line search in the constraint setting, right? Okay, Any more questions about this? Anyone want me to try anything else weird before we switch back? Okay.
Are there similar situations you could show where the full Newton outperforms Gauss Newton? Like I assume there are.
Yeah, so what'll happen, right? So full Newton has theoretically faster asymptotic convergence, meaning like when you're really close to the answer, it'll zoom to the solution faster once you're close. When you're far away, though, is when these problems happen, right? All these problems are sort of far away problems. And when you're far away, that extra curvature term is really not helping you, is basically the message. So there's definitely situations you can cook up where full Newton will converge in fewer iterations. But I think in general, there's not really situations where like Gauss Newton will get stuck, where Newton won't get stuck. I think generally speaking, Gauss Newton's tends to be in these kind of situations more robust if it's a little bit slower. That's kind of my hand wavy, you know, sort of intuitive sort of explanation for what's going on.
Thanks.
Sure. Okay. Back to the notebook.
Professor, so basically it looks like Gauss Newton does all the good things that Newton's supposed to do. So like what are the pros and cons of using Gauss Newton?
Yeah, so I mean, it always is it varies based on your specific problem, but basically Gauss Newton is cheaper and might be more robust on very nonlinear constraints. But it has slower convergence, so it might take a few more iterations. That's basically the summary. Does that make sense?
Okay, yeah, thank you.
And yeah, so we can write that down here.
What does people generally do with like initialization? It seems like it's pretty important for the solver.
It is, yeah. So this is sort of this is sort of where you get into voodoo-y, you know, dark art sort of vibes. So when you're doing this stuff on non-convex nonlinear problems, like we usually end up with in these robotic like optimal control problems, the initial, I call it the initial guess problem, is huge. And generally speaking, this is where you have to use all of your intuition and like sort of engineering insight to sort of give it a good initial guess. And yeah, the better you can do with the initial guessing, the better these techniques all work, because they're all local search techniques, right? So yeah, you will get experience with this. But yeah, for now, let's just say it is a bit of a dark art, and you have to sort of like, you know, do the best you can engineering a guess before you kind of plug it into these methods.
Thank you.
Yeah. Okay, so just to summarize then the example which you'll have the code for, we sort of started at a couple different points, I think like -1, and then -3, 2, and then this one, you didn't get stuck. And Gauss Newton doesn't. Okay. So yeah, and then just takeaway sort of notes. You, in general, still have to regularize. even if the Hessian of the objective is strictly positive definite. And yeah, Gauss-Newton's often used in practice, and especially in optical control. Okay, cool. So next up, we are going to talk about, so we did equality constraints, and typically in our context, that's going to mean the dynamics, right? So the dynamics are typically dealt with as equality constraints, have to obey physics. Sometimes you might have an equality constraint for like a goal constraint, a goal state you want to hit at the end of your horizon or something like that. That's another kind of thing that might show up as an equality. Now we're going to talk about inequalities. And these typically show up. Yeah, go ahead.
Yeah, so the equality dynamics constraints, are you basically saying then like at each time step, the dynamics equal, you know, the next iteration?
Yeah, something like if you've got your discretized dynamics, like we talked about a couple of classes ago, xk plus 1 equals f of xk uk, that's it. That's your dynamics constraint, right? So you'll have like your whole x trajectory and your whole u trajectory will be your decision variables in your optimization problem. And you have a whole bunch of equality constraints at each time step saying xk plus 1 has to equal f of xk uk. That makes sense?
So then do you always need like some sort of time horizon that we're talking about in an optimization problem?
Generally, yeah. I mean, there are so-called infinite horizon problems that you can write down, but you can't really solve those numerically super nicely.
Yeah.
Most of the time, right? So for finite horizon problems, which is usually what we're going to deal with, that's exactly the setup. Okay, so here, similar to before, we're going to be minimizing an f of x, but now we're going to be talking about c of x greater than equal to 0 instead of equal 0, right? And we're just going to right now focus on inequality only. You can obviously combine the two, right? In general, we will. And in our context, this kind of inequality thing, there's kind of two main places these show up in control problems. One is like torque limits on your actuators or thrust limits, right? This kind of stuff. So actuator limits. And the other one is like safety constraints, like keep out regions or obstacle constraints, right? So those would be like state inequality constraints. So those are kind of that's what you should have in your head when we talk about these. Again, we'll just do the inequalities for now. And in general, right, you're going to combine these with the stuff we just talked about before. Okay. So now we're going to talk about similarly first order necessary conditions for these guys. And it's really similar, but the intuition is super similar, but the math looks quite a bit different. Okay, so same deal as last time. We have grad f equals 0 in the free directions. So in any direction you can feasibly move, the gradient has to be 0. But if you're up against a constraint where you can't move in that direction anymore, then you can have a non-zero gradient in that direction. And then 2, c of x has to be greater than equal to 0 instead of equal like before, right? So almost the same sort of like, setup, same intuition. Now I'm going to write down what these look like in math, and then we'll talk about them a little bit because they are kind of different. So
A quick question.
Yeah.
So for the first condition, because in this case, the constraint is not like equality, doesn't that mean you can technically like kind of move in the constraint direction too, like when you're inside? Or does that not matter?
So when I say free direction, I mean any direction you're allowed to move legally according to the constraints. Does that make sense?
Okay, got it. So it could include like the constraint directions, but like inside the set, basically?
Yeah, it means if you're in the interior of the set, cool, you're good. If you're at the boundary of the set, then you can't push any more in that direction, right? But you could go the other way, right?
Yeah, that makes sense.
So it's a little subtle, but yeah, it just means, what I mean by this is any direction that's legal with respect to the constraints, the gradient has to be 0. And any direction that is illegal with respect to the constraints, you're allowed to have a non-zero gradient in that direction, right? So that's the intuition. It's like you're going to do the best you can subject to the constraints. So like any direction you can feasibly move, the gradient's got to be 0 in those directions, right?
Yep.
Okay, cool. So let's try to write that down now mathematically. And I'll just start doing it. And then, so the first one looks really similar to what we had before, the sort of gradient condition. So this is exactly what we had before. This is called stationarity. And that's sort of, again, like fixed point, right? Stationary, fixed point, flat spot, gradient equals 0, right? That's so this all mean the same thing. The next one is just like before, but an inequality now instead of an equality. So C of x greater than or equal to 0. And this is called primal feasibility. So feasibility, sort of, we know what that means, right? It's feasible with respect to the constraints. It's not violating the constraints. Primal refers to the x variable, in contrast to dual, which refers to the Lagrange multiplier lambda variables. So that's where that comes from. The next one we're going to have is, in this context, in addition to primal feasibility, in addition to the inequality on the constraint, we also have an inequality on the Lagrange multipliers. So lambda has to be greater than or equal to 0. And this one, as you might expect, is called dual feasibility. And this is coming from the fact that if you're an inequality constraint, it's sort of one-sided, right? And you can intuitively think of the Lagrange multiplier as like the force pushing you away from the constraint, right? That's keeping you from violating the constraint. So in the inequality case, because the constraint's one-sided, that Lagrange multiplier force is only allowed to push you in one direction away from the constraint. It's not allowed to pull you closer to the constraint, right? And if you like flip sides and you're on the other side, then that lambda would flip directions. So in the equality constraint case, this force, can be in either direction. It can push or pull because it's trying to keep you on that surface. If it's one-sided, it's only allowed to push you away from the surface in kind of one direction. So that's why it's got that greater than or equal to 0 flavor. And then the last one looks like this. This is called complementarity. And this is basically encoding switching behavior. So this is saying if the constraint is active, meaning you're on the constraint surface, then C of x is equal to 0. And I'm allowed to have a non-zero Lagrange multiplier. So if C of x equals 0, I'm on the constraint surface, then lambda's active is non-zero. If I'm off the constraint surface, C of x is non-zero, then lambda has to equal 0. I'm not allowed to have any Lagrange multiplier if I'm not on the active constraint. So that's what that last one encodes. So this whole set of conditions here, this whole set of first order necessary conditions are called the Kkt conditions. These are the real Kkt conditions.
Should the first equation be grad f plus?
So yeah, that's a good question. Why do you think that?
Because you just take the derivative of like f plus, like how we did before.
Yeah, so I didn't write down the Lagrangian yet, right? So last time it was plus, and that was sort of with respect to like me writing. So I guess the first question is, could it have been minus last time?
I guess that one doesn't matter because it was supposed to be equal to 0.
Yeah, exactly. So it doesn't matter actually. Like if I put it before, I could have put it as a minus sign and then it would have just flipped the sign of lambda, right? So because the sign of lambda doesn't matter in the equality constrained case, it doesn't matter. You could make it either sign. Here, the sign of lambda actually matters, so we have to be careful with this. It turns out you can actually do it either way, but it changes the signs on the inequality constraints. So in this particular,
flip the dual visibility, right?
Yeah, exactly. So if I made that a plus sign, then I would have to make lambda negative in the dual feasibility condition. That's exactly right. So yeah, basically here the signs matter. So like it's just an arbitrary choice, but you have to be consistent with it. So I've decided to make everything positive, like C of x positive, lambda positive, and therefore that has to be a minus sign, it turns out. If you flip one of those, then you can flip them around, right? Kind of arbitrarily, but you just have to sort of follow through.
Professor, another quick question. You mentioned that we can have lambda non-zero only when like it is on the active region on C of x. But when we're considering C of x greater than 0, can't we have lambda like push us even if we're not on C of x?
No, that's sort of not what you want, right? So like then it's affecting the answer to the optimization problem, right? It's sort of like messing with your answer and you don't want that, right? If I'm not on the constraint surface, the constraint shouldn't be affecting my solution. Does that kind of make sense? So I'll write down some more of this and we'll get more into it. But yeah, feel free. So if the constraint is active, so C of x equals 0, then I can have lambda positive. And the way to think about this is when the constraint's active, I'm in the exactly the same as the, this is exactly the same as the equality case, right? That we did before. Then if I have the constraint inactive, so this would be C of x, positive, strictly positive. So I'm not on the constraint surface. Then lambda has to equal 0. I'm not allowed to have anything in here. And this is making it the same as the unconstrained case. Does that make sense on that last question? So basically, if I'm not on the constraint surface, if I'm in the interior, then it's exactly the same as if it were an unconstrained problem. So that Lagrange multiplier term should drop out. Does that make sense? So
then now we're just like directly moving towards del f being 0 rather than. Okay.
Yep. If the optimum is in the interior of this constraint set, then the constraint's not doing anything. So that whole constraint term doesn't matter anymore, right?
Okay, makes sense.
Does that sound good? So yeah, so basically if you're in the interior, the constraints are inactive, it should look just like the unconstrained case. And then if you're on the constraint, it looks just like the equality constrained case. And that complementarity condition basically enforces that switching back and forth.
Oh, what happens if the constraint is violated in this case?
So then it's active, right? Or it should be. And there's more to say about that, I guess. So let's see. If it's violated, what exactly happens in a solver when it's violated depends on the details of the solver implementation. We're going to talk about this kind of right now. So it depends exactly what you do. These conditions, all these conditions are telling you are the necessary conditions for a solution. So they're just telling you what's true at the solution point. They're not necessarily telling you what to do far away from a solution point. Does that make sense?
I see, yeah.
Okay, so what we're going to kind of get into now is sort of algorithms for solving this stuff, which are unfortunately a lot more complicated. than the last case. So much harder than the equality case. And in particular, in the equality case, I could basically just do Newton on the Kkt conditions, right? Now I can't do that, it turns out. If anyone has any insights into why, that would be fun. Anyone have any thoughts on why?
Because of the sharp discontinuities in the complementarity conditions?
Yeah, there's sort of bad things buried in that complementarity condition, which we can talk about. And there's lots of options here. And we're going to kind of go through a few now. Okay, so here's a whirlwind survey of a bajillion ways of solving these kind of inequality constraint problems. The first one is called an active set method. And the idea here is if I magically have some like oracle that can tell me which constraints are active and inactive, then I can just solve an equality constraint problem, right? And not have to worry about all this stuff. That sounds kind of weird and stupid, but it turns out that there are situations where you can make very good guesses at which are the active constraints. And then, maybe you guess wrong a couple times, but you have like good heuristics for figuring out the active set. And then you just have to solve a handful of equality constraint problems. That can work really well, it turns out, and depending on how good your guessing is, basically. And there are good instances of this in control. So yeah, the advantage here is this is super fast if you have a good heuristic for guessing. And then if you don't have a good way of guessing, it's very bad. So good example of this in robotics is the MIT DRC team that sort of did Atlas back in like 2014, 2015 or so, when they were sort of competing for that DARPA challenge. They developed a custom active set QP solver for their robot. And they had a bunch of like really good heuristics for guessing the active set. And they guessed it right like 95% of the time. And in the other 5% of the time, they could get it right in like one additional guess. And they, as a result, were able to like control that robot at like, they could run that solver at kilohertz rates. So big win. So in particular problems, you can sometimes do this really well, and that's a huge win. Okay, so other ways to do this are barrier or interior point methods. And these are basically the same thing. And the idea here is you're going to replace inequality constraints with a so-called barrier function that blows up to infinity. You put this in the objective. That's going to kind of blow up to infinity at the constraint boundary. Okay, so this looks like if I have my min of x subject to c of x greater than or equal to 0, I'm going to take this and I'm going to replace it with min over x f of x plus, or minus, I should say, a term that, so that the standard barrier function is called the log barrier. I'll draw a picture of it. So I equals 1 to m for m constraints. Let's write this down and then we'll talk about it. Okay, so that's what that looks like. So the idea here is if I plot this sort of, so if the x-axis here is like c of x, and then this is minus, I guess I can just plot this as x. So whatever the argument of the log is, so x here. So minus log of x is going to kind of be more or less 0. And then near x equals 0, it's going to blow up to infinity and like kind of asymptotically go to infinity as x gets to 0, right? So the idea is it's pretty much flat far away from 0 when x is positive. So it has minimal impact on the objective function when you're not near the active constraint. As you get close, it's going to blow it up to infinity such that that objective is just huge, right? It's basically a gigantic penalty, infinite penalty of being sort of too close to the constraint. And then that 1 over rho in front is like basically lets you dial in how steep it blows up. Okay, so does that kind of make sense to everybody? So these are kind of the gold standard. They work really well for sort of small to medium size convex problems. So they're the thing to do if you have like a convex QP or LP or something like this, and it's not too huge. These are the way to go. But for non-convex problems, which are kind of most of the ones that we're going to deal with, these are really, you can make them work, but it's really hard. And it needs a lot of extra tricks and hacks to make them work on non-convex problems.
Question on this barrier method. So does this mean that it will probably never touch the boundary if it's log? Like greater than equal to 0 basically means greater than 0 in this case.
Yeah, so it's a strict kind of greater than, but what happens, you kind of end up cranking on that rho term as the solver converges, and you can basically push it all the way over to like pretty tight tolerances to like almost machine precision. So okay, definitely so like 8-10 decimal places. So you can basically get the answer to be as close as you want to as many decimal places as you want by playing around with the rho.
Okay.
Does that make sense?
Yeah.
Okay, cool. Okay, so barrier functions, interior point methods, same general idea, great for convex problems. Let's talk about another one. So penalty methods, similar idea in spirit, but a little different flavors. So here we're gonna replace the inequality with an objective term that penalizes constraint violations. Okay, so kind of here what this might look like is min f of x subject to c of x greater than or equal to 0 will get turned into something like min of f plus, so the standard one as a quadratic penalty. So that looks like this. And this is like element-wise min, right? Kind of idea in there. And if I plot this, what you're going to get, right, is something that's, this is x, and then this is sort of min 0 kind of x squared. It's going to be 0 all on the inside here, and then you're going to get basically a quadratic penalty when it's infeasible, right? Okay, so what to say about this? Super easy to implement. but has lots of numerical issues. And what else do we say? It's sort of as a result, of that, it's difficult to get sort of good high accuracy constraint satisfaction. Okay, so we are right at time there. So this is like not a terrible place to take a break. So anyone has questions, happy to chat about those. Otherwise, we'll pick it up on Tuesday. And also, we should be getting out. So hopefully everyone tried the homework 0. If not, do it, please. And the real homework 1 is going to go out tomorrow, probably. And you'll have 2 weeks to do it. And we'll have kind of full set of office hours and stuff next week. So I'll stick around for a little bit if anyone has questions. Otherwise, we'll catch you guys on Tuesday.
I have a quick question.
Sure.
So you mentioned that the barrier method is good for small to medium problems. What do small to medium problems like?
Yeah, that's like kind of ambiguous. It turns out like it really depends on, it depends in particular on problem structure in a big way. So, I mean, practically speaking, like anything up to a few thousand variables is probably fine and not a big deal with those methods. If you get to stuff with like millions of variables, that's definitely large and too big for like an interior point method. In the middle there, like more than a few thousand and less than a million, that's sort of ambiguous and it depends on the particular problem. But yeah, I would say like safely anything less than a couple thousand variables is fine.
Okay, thanks.
Small to medium, yeah. The honest answer there is it depends on your computer. And as computers have gotten better and better, the definition of large scale optimization, keeps shifting. Okay, yeah, so there's some more stuff to say about this, which we're going to get to next time. So we kind of ran out of time today.
That's a really quick.
Yeah.
I'm having some trouble kind of visualizing the diagram that you had initially. So when you were talking about the level curves and the curve with those level curves, I guess I follow everything numerically. I just don't understand how visually that curve is supposed to follow those level curves. So the way I'm thinking of it right now is that.
So we're talking about this picture here?
Yeah.
Okay, yeah. So the idea here is those level curves are like telling you, I mean, that's the shape of the bowl, right? And then the constraint is some line that you have to be on, right? You have to satisfy that equality constraint. So like intuitively, what you want there is you want to be as close to the real minimum as you can get while being on that line. Okay.
So in this case, if I had a bowl and if I drew, like if I were to say like draw a line on that bowl at any point in that bowl, the goal would be to find the point that was closest to the bottom of the bowl to that line that's drawn on the bowl.
Yeah, that's pretty much it.
Okay, so the function that we try to minimize, or like the constraint, that function has to lie on those level curves. It can't lie away from the level curves.
I mean, I can draw these level curves. I can draw as many level curves as I want, right? This is just like the idea there is it's just giving you, like this picture is me looking down at the bowl from above. Right. I was trying to give you a picture of like, the shape of the bowl, right?
Okay.
So what this is saying really is that another way of thinking about, there's a bunch of sort of equivalent ways to think about this idea of like what the free directions are, right? On this. So the intuitive idea is that I need the gradient to be 0 in any free direction that I'm allowed to move, right? So that means here in this picture, grad f can't have any component that's parallel to that line, right?
Okay.
Does that make sense?
Yeah.
Okay, so another way of saying that, if it can't have any component parallel to the line, then it has to be totally perpendicular to the line, right?
Oh, okay. Okay, yeah, that makes sense.
So that's kind of the idea. Another way of saying that, so if grad f, it has to be totally perpendicular to the constraint line, that is also equivalent to saying the line at a solution point, the line has to be perfectly tangent to the level curve.
Oh, okay. Yeah, that makes a lot of sense. Okay.
Yeah, okay. So there's like there's like a half dozen completely equivalent ways of saying that thing. And I think I just said them all over the course of this. So hopefully one of those kind of clicks, or a few of them click now. Yeah.
Okay, awesome. Yeah, thank you so much.
And then, yeah, literally this Lagrange multiplier idea here, it's literally just a mathematical way of writing that idea, right? So it's saying like, grad f and grad c have to be parallel is what that equation literally says. And the lambda is just saying they have to be parallel, but they don't have to be the same length. So lambda is there to sort of make the lengths match.
Right? Okay. Yeah. Okay, that makes sense. Awesome.
Cool. All right.
Thank you.
Yeah, you got it. All right. Anybody else?
I just got one more question. Yeah, so you mentioned about the three methods of solving this inequality KKT. I wonder if it makes sense to use the second and third method as an initialization for the guess for the first method.
Sorry, so we're talking about these guys?
I think it's down there. So I'm just trying to, I wonder if it makes sense to use the barrier method or the penalty method as an initialization, and then we can guess for what the active states are. And then we can use the active states method.
Yeah, so this is a great idea. This is actually very commonly done in practice. So a lot of the times what you'll see is one of these other methods will be used until you get pretty close to the answer, and you can then know with high confidence what the active set is. And then you'll switch over for the final sort of couple iterations to an active set method. That's often called solution polishing, and it's a super common trick.
Yeah, got it, thanks.
In fact, yeah, have you ever used OSQP?
Not really.
Okay, so yeah, this is a common thing in many of the industrial strength solvers. So like in particular, I was gonna say OSQP, which is one of the best QP solvers out there, that if you ever have to solve a QP, it's one of the main ones you would use, does this. It uses some penalty-ish things for a while, and then it basically switches to an active set at the end once it's really close.
Right,
so yeah,
thanks.
Good idea.
Yeah. So I have a quick question about the Kkt conditions for the inequality case.
Okay.
So you mentioned there's I just wanted to ask if you could repeat kind of the intuition behind the four constraints. I think I understand the complementarity, but yeah, I just if you could go over the intuition behind the other ones.
Yeah. Okay. So the first one is just gradient equals 0, like we had before, right? So that first stationarity condition, it's the exact same thing we had in the equality case up here, right?
Yep.
Okay, so that one hopefully is clear.
Yes.
Okay, yeah, so the first one is literally the same thing we had before with the equality case with the Lagrange multiplier. The next one is just saying that you have to respect the constraint, right?
Yeah.
Yep. Okay, all right, so the last two are the tricky ones. So what's going on with the last two? So you said you kind of get the complementarity, that's sort of encoding the switching thing?
Yeah, okay. I think so.
So the combination is kind of altogether what makes it work. But basically, in the inequality case, right, the constraint's kind of one-sided. You can think about it like I've got, so if like in this picture up here, where I have this line, instead of having to be on the line, I'd have to be on one side of the line, right?
Right.
That's kind of the idea. Okay, so because of this one-sided situation, in the equality case, that Lagrange multiplier can point either way, can have either sign. And the idea there is grad, so what's the right way to say this? So remember this whole idea about the gradient having to be 0 in the free directions?
Right.
Okay, so in the inequality in the equality case, like grad f can have, grad c can be like pointing either way, right? It doesn't matter with respect to this surface. In the, so like in particular in this picture, right, you see the little green grad c and the little red grad f.
Right, yeah.
They can point opposite ways, whatever, it doesn't matter, right? In the inequality case, remember this whole concept of free direction. Well, I can move in one of those directions, one of those normal directions to the constraint surface in the inequality case. I can't move, I'm like free to move any way I want this way, but not this way, right?
Right.
And so that like signed lambda thing there is kind of getting at that. It's saying like, those things have to be parallel and they have to be pointed the same direction. They're not allowed to point in opposite directions, because that would mean I could still make progress going the other way, right?
Right, yeah.
Does that make sense? Okay, cool. Yeah. So that's getting across the one-sidedness of the inequality case. That inequality on the lambda. And then the last one is getting at the switching, active versus inactive.
Right. Okay, thank you.
That's sort of cool. So yeah, this is like, I mean, you can get some intuition for this. It's not so terrible. There's actually like a really nice intuitive way to understand this from mechanics that's going to be on the first homework, which is like dealing with like a falling brick. So it's like in that case, the constraints are like the C of X is the ground, and like you're throwing a brick, it's flying through the air, then it's going to hit, like think about it like a brick hitting ice and sliding. So in that case, the inequality constraint is the ice, the surface of the ice. You're not allowed to go through the surface. And the Lagrange multiplier is the normal force that's holding you up, that's pushing you up and preventing you from falling through the ice. So in this case, it's like super, super clear like where it all comes from. Basically, like you have to be above the ground. You're not allowed to be under the ground. So that's C of X greater than or equal 0. Then the lambda positive thing is saying the ground is only allowed to push up on you, not pull down on you, right?
Right.
And then the complementarity is saying that you can only have a force if you're actually touching the ground. You're not allowed to have any force if the brick's in the air.
I see.
And it's like super, super intuitive when you think about it as like simple physics, right? But it's exactly mathematically describes that scenario.
Cool, thank you.
All right, cool. Anybody else?